So we need to find the efficiency of this engine and compare it to the ideal efficiency. And then we need to find the change in entropy of the universe for the engine, and then find the change in entropy of the universe if the engine was ideal. So we have our work done. So 550 joules of usable work. And then we have QH. So this will be the total heat input of 2,500 joules. And we have the exhaust temperature. So this will be 650 Kelvin. And then we have the intake temperature, T sub H. This will be 970 Kelvin. So for part A, we can say that the efficiency actual is going to be equal to the work over Q sub H. So this will simply be 550 divided by 2,500, and we're getting 0.22. So this will be 22% efficiency. We have the ideal efficiency. This is going to be equal to 1 minus T sub L, the exhaust temperature divided by the intake temperature, and this is going to be 1 minus 650 divided by 970. And we have that the ideal efficiency will be 0.33. So if you compare this, E actual divided by E ideal is going to equal 0.22 divided by 0.33. This is, of course, 2/3, or 66.7%. So essentially, the engine is 66.7% of its ideal efficiency. So essentially it is 66%. If this engine was ideal, rather the actual engine only has 66.7% of the efficiency of the engine if it was ideal. This is not the efficiency. This is just a ratio between the actual efficiency and the ideal efficiency. And for part B, so this will be your answer for part A. For part B, they're asking us for the total change of entropy of the universe of the actual engine. So we should first find QL, which is going to be equal to Q sub H minus work. So 2,500 minus 550. And this will give us 1,950 joules. Delta S is going to be equal to the change in entropy of the input plus the change in entropy of the output. So this will be equal to negative QH T sub H, and then, of course, positive Q sub L T sub L. And we can say that this is going to be equal to negative 2,500 divided by 970, and then plus 1950 divided by 650. And we find that the change in entropy of the universe is going to be equal to 0.42 joules per Kelvin. So this will be part C. For part B, that will be part B. For part C, for the Carnot engine, Q sub L equals Q sub H 1 minus E Carnot. So the ideal efficiency. And we find that this is going to be equal to Q sub H T sub L over T sub H. So again, we have the delta S is going to be delta S input plus delta S output. And we can say that this is going to be equal to negative QH divided by T sub H, plus Q sub L divided by T sub L. So again, the same exact formula. However, now we're going to substitute for Q sub L and say that this is going to be equal to negative Q sub H over T sub H plus Q sub H T sub L over T sub L T sub H. So once these cancel out, we only have negative Q sub H divided by T sub H plus Q sub H divided by T sub H. This is going to give us 0. So the change in entropy of the Carnot engine is 0 joules per Kelvin, and that's what makes it the Carnot engine, because again, it's ideal. The Carnot engine is ideal, which means that no energy is going to be wasted due to entropy, essentially. So the change in entropy of the Carnot engine is, of course, 0 joules per Kelvin. This will be our answer for part C. And that's the end of the solution. Thank you for watching.